Dear friends, I am Professor Atula. Here I am presenting the efforts taken by Sri Lankan geotechnical engineers in the reduction of landslide risk in Sri Lanka. So this is part of the time capsule project of ISSMB. This presentation is in 4 parts. So this is part 1, where I present the geomorphological and geological background of Sri Lanka. Sri Lanka is located between northern latitudes of 5 and 10 and eastern latitudes of 79 and 82. It occupies an area of 65,000 square kilometers, stretching 435 kilometers from north to south and 224 kilometers from west to east. The climate is semi-arid to mild. This variation is due to the central highland region here, and this is surrounded by extensive low-lying area close to mean sea level. And annual rainfall is contributed by 2 monsoons, 2,500 to 5,000 millimeter rainfall coming from southwest monsoon, which occurs from May to September, and 500 to 2,000 millimeter rainfall from northeast monsoon from December to February. Mean annual temperatures are about 27 degrees in the lowlands and 15 degrees in the highlands, and we have a forest cover of about 23.75%. As observed in this map, Sri Lanka falls in the area of highest rain-induced rainfalls. Along with this Asian region, we are located in the area of high rain-induced rainfalls. So our landslides are all triggered by excessive rainfall. Here we have the landslide map, right? Landslide map with this legend, and it matches very well with the slope elevations, ground elevations, elevation ranges, and the slope anchors. And National Building Research Organization, which is the government authority on landslide, has developed landslide hazard zonation maps, which I will elaborate a little later. So these 2 maps, basic maps, matches well with the landslide hazard zonation maps. Landslides with the higher risk landslides are in this high risk of landslides are in the areas of dark brown, then less in the lighter brown, and in the green areas this is much lower. So these 3 matches very well with the actual landslides occurring. So in Sri Lanka, landslides mainly occur in the central highlands, and they are triggered by excessive rainfall. So this is again a record of landslide events that are causing deaths and missing people from 1974 to 2019. So this is the rainfall record compared with the landslide occurrences. So landslides are occurring in the areas of high rainfall as illustrated here. In Sri Lanka, we have high elevation differences changing from near mean sea level to about 3,000, 4,000 meters above mean sea level, occurring over a very short distance comparatively. So we have a road network going through hilly terrains and also a rail network, and people are living everywhere, all parts of the country. So minimizing the landslide risk in this road network and the populated areas is a great challenge faced by the Sri Lankan engineers. Talking about the important geological background, sloping grounds in Sri Lanka are formed of rocks of different level of weathering, residual soils, and colonial soils. Rocks present are mainly metamorphic. Principal rock types are gneiss, charnokites, marble, and quartzite. In these rocks, we have banded structures with one or more joint planes. joint planes will remain as relic joints in the weathered product, the residual soil. A typical situation is well illustrated by this photograph taken from the cuttings of the Southern Expressway. Here in this road cutting, the natural slope was cut to make the way for the expressway. So in this cutting, this area, it is rock that is exposed. It is unweathered Charnacotic rocks. Just next to it is gneissic rocks, which have now weathered to form a lateritic soil. Now in between, in the matrix of weathered material, you have Charnacotic soil. If the parent rock is Charnacotic, it has not weathered, it remains as a rock, while the surrounding gneissic rocks have weathered into this residual soil. Such high heterogeneous conditions with abrupt changes are quite common in Sri Lankan slopes. So in this section, again, in the same Southern Expressway cutting, you have Charnacotic rocks embedded in a matrix of the lateritic soils formed by weathering of gneissic rocks. And down here, you have a whitish, highly vulnerable clay layer, which is the weathered product of a feldspar gneiss initially. So such highly heterogeneous soil profiles are quite common in Sri Lankan slopes, and these different materials will have contrasting permeabilities and contrasting shear strength characteristics. This is an illustration of joints, highly jointed rock, closely spaced joints. So these joints will remain in the residual soil, and then we call them relic joints. So they are weaker points in the residual soil. So you can see toppling failures like that in a cut slope, or sliding failures like that again in a cut slope through the relic joints. Many of these slopes are with a low groundwater table during the periods of dry weather. Prevailing high metric suction make them stable. Near vertical cuts of height even 10 meters or more would remain safe under these conditions. Infiltration of rainwater, loss of metric suction, and the development of porch water table conditions would occur with rainfall and make the slopes unstable. This process can be modeled numerically. We have done that in a number of research projects. Most of these landslides occur in the upper colluvial layers, or in the boundaries of colluvial and residual layers, or in the boundaries of residual layers and the weathered rock underneath. Two most important characteristics in this modeling process of infiltration is the soil water characteristic curve, showing how the matrix suction will vary with the volumetric water content, and how the permeability will vary with the matrix suction. We have established these relationships for different types of Sri Lankan soils using experimental procedures like the method of continuous measurement and the pressure plate apparatus. And also we have used existing empirical relationships relating these to the particle size distribution and plus the characteristics. So here shows a comparison of the soil water characteristic curves obtained by different techniques. So we use these to model the infiltration into sloping grounds in Sri Lanka. These are results of one such modeling exercise. So this is a typical cut slope, and the boundary conditions are given here, and the slope infiltration into the sloping ground was modeled, and the resulting changes in the matrix suction at these two sections, section 1 and section 2, were established. So this is the case where the slope is made up of complete uniform material, uniform residual soils. So that is the groundwater table. The top part is unsaturated with some metric suction. So we have adopted minus 100, maximum of minus 100 metric suction in the upper part. The coefficients are positive below the groundwater table. The effect of infiltration was studied and presented in the form of variation of the pore pressure profiles at section 1 and 2. So this is the case of highly weathered rock lying below the residual soil. So in the case of uniform residual soil formation with the rainfall, first day metric suction is lost up to that depth, second day further deeper, and like that for the 5 days. So then the water that infiltrated through the saturated pores has caused a slight increase of the groundwater table. So this is in section 1. In the section 2, with the lateral downward movement, the destructions are much more. So with daily rainfall, the metric suctions were first lost up to that, then that, like that. And at the same time, there is a greater rise of the groundwater table. So with the prolonged rainfall at these sections 1 and 2, pore pressure regime is subjected to this range. So we can model this and we can incorporate this in the stability analysis thereafter. If there had been a rainfall of much greater intensity, now you can see at the upper levels, metric suction is not just reduced from 100 to 0 as in the previous case, but there are positive pore pressures developed at the upper level and at the lower level also from the beginning. So this we refer to as a purge water table situation. The rise of groundwater table here is little greater than the previous case, but minimum. So the main destructions are happening near the surface, loss of metric suction and development of purge water table situation. At lower levels, there could be a high rise of the groundwater table. If the slope is made up of residual soil overlying weathered rock, there's a boundary of contrasting permeability. Under these conditions, water may not infiltrate down to a layer of low permeability, but there can be a pore pressure build-up as seen here, right? So at the lower levels also, water may not penetrate into the layer of lower permeability, but there can be a pore pressure build-up at the bound of contrasting permeability. So there I showed you how the infiltration will cause a reduction of metric suction and development of purge water tables. So the shear strength equation is given by that. So with the loss of metric suction, shear strength would be lowered. With the development positive pore pressures, it would be lowered. So the factor of safety is the ratio of shear strength to shear stress to be mobilized for equilibrium. So with the reduction of that, factor of safety is decreasing. So we have established that for this kind of a typical slope under different conditions, with the continuous rainfall, factor of safety decreases. So in a homogeneous slope, starting with that, with a 5 mm per rainfall, hour rainfall, it is dropping like that. With the heavier rainfall, it is dropping much faster. So when you have contrasting layers of permeability, so it may start with a heavier, larger value, but it is dropping much faster. So this is for a slope of gradient, 1 vertical to 1.26 horizontal. We have done this for slopes of different gradient, done for 1-to-1 as well. So in that, what we realized or what we illustrated was that whatever the slope gradient, these events will take place and eventually the slope may reach instability. So these are typical critical failure surfaces for uniform slope and this slope with highly weathered rock. So they are shallow failures basically. We can illustrate that with various experiences in the country. This is the cut slope, cut very steep as a bypass road in the Colombo Candy highway. Immediately after the cutting, it looks very nice, no signs of failing. Just 2 months after that, just when the slope was exposed to the very first rainfall, you can see the destructions that have happened. So with the further rainfall, there can be prolonged further failures. So this is another slope, cut slope in the Southern Expressway. Slope was cut, but due to a contractual problem, the drains were not installed immediately. So you can see there's a colluvial layer up there and the lateritic soils there. And this situation here, whitish clay, due to that high feldspar-rich initial soil. So you get highly contrasting conditions in a cut slope. Now here, during a period of rain, during a rainstorm, you see water moving in an uncontrolled manner, heavy flow coming from further up slope. So it was like that for a few years, so it ended up like that. The landslide that initiated ended as a flow, bringing all the debris to the expressway constructed. And now you can see with this elevation, so there is rock, everything right up to the rock has moved. The infiltration to the rock is prevented. Rocky water is not infiltrating into the rock, so there is heavy pore pressures developing at the soil rock boundary, and all the material, all the soil up to the rock has flowed down. And you can see highly non-heterogeneous conditions because the rock is not present everywhere. Rock is present only in this region. So this is another event in the Southern Expressway. Expressway was constructed, all the drainage measures were done, but there were problems in the maintenance of the drainage. So there was a problem in the drains here. So as a result, there was water leaking into the ground. And this cat was seen around 9 o'clock in the morning. So expressway authorities stopped the traffic in that particular lane and they were vigilant. By 5 o'clock, all this mess moved down, causing much destruction. You can see here that the depth of the failure surface is quite shallow, right? That whitish clay soils were here. So this was where initial destruction has happened, right? So it flowed down as debris covering 2 lanes of the expressway. So this happened after few days of heavy rain, right? But the groundwater table has not risen. The matrix section is completely lost over here. So these are some further pictures of landslides taken place in different parts of the road network. Whatever the famous landslide in the railway track, I will talk in detail about this later. So all these landslides were subsequently rectified. So these were some other landslides that happened in natural slopes in the country, not the transport network, right? You can see they are massive. There is an initiation area and the material has flowed down, causing massive destruction in the flatter area as well. All these landslides have taken place after days of prolonged rainfall. You can see this Poonagala Miriabedda landslide. The rain gauge station was at Poonagala, right? So after these days of rainfall, it occurred, right? So that's a common feature in all these landslides. Right, so with that, I conclude the first part of the presentation. Next, I will go to the second part where we talk about monitoring. Thank you.